into the incredibly tiny, super fascinating heart of matter, the atom. Now, look, if you've ever stared at a periodic table and just felt totally overwhelmed by all those floating numbers, well, you are exactly in the right place. By the end of this, the math of subatomic particles is going to make complete intuitive sense. So let's unlock the atomic vault together.
Okay, let's dive into this. Have you ever actually stopped to wonder what fundamental trait gives an atom its ultimate identity? Seriously, think about it. If I hand you an atom of gold and then an atom of oxygen, what is the single, absolute, non negotiable property that dictates exactly what they are? Just keep that question tumbling around in the back of your mind as we kick things off, because the answer is literally the key to unlocking the whole shebang when it comes to chemistry.
All right, here's our blueprint for today's explainer. We're going to start with the atom's identity card, peek inside the atomic vault, run through the particle math formula, and then solve a really cool elemental puzzle. After that, we'll look at ions, gaining and losing, and finally wrap up with the ultimate subatomic match. Okay, Chapter 1, the atom's identity card, discovering the subatomic fingerprint. Let's get into it. So let's travel back in time just a bit to 1913. There was this brilliant scientist, Henry Moseley, and he ran a totally groundbreaking experiment. He basically took about 32 different elements, ranging all the way from aluminum to gold, and he literally bombarded them with cathode rays. Basically, he just shot high-energy electrons right at these pieces of metal. And when he did that, bam, the metals emitted distinct X-rays. But here's where it gets really cool. Moseley noticed that the frequency and wavelength of those specific X-rays were directly proportional to a fundamental property of the element itself. He essentially discovered a bulletproof way to read an element's secret identity, what we now call the atomic number, or Z. So the crucial point is that the atomic number, RZ, isn't just some random filing label. It's actually the exact count of protons securely sitting inside that atom. It is the ultimate identity card. The entire modern periodic table is organized purely by the Z number. For example, a Z of 6 means exactly 6 protons, and that means it's carbon. End of story. 7 protons, that's nitrogen. If you change that atomic number, you literally change the entire element. Mind-blowing, right? Moving right along to Chapter 2 inside the atomic vault: protons, neutrons, and nucleons. Now, I want you to picture the center of an atom, the nucleus, like a heavy-duty, highly secure vault. Inside this central vault, you'll find the heavy particles. And in chemistry, we use a really specific collective term for them: nucleons. A nucleon is just the umbrella term for the positively charged protons and the neutral neutrons that are tightly packed and securely housed right in the core. So while those tiny lightweight electrons are zipping around way out on the outside, the nucleons are the heavyweights, locked safely inside that atomic vault. And because the protons and neutrons are the actual heavyweights of the atom, they are what determine its overall mass. Which perfectly brings us to our next big concept: the mass number, represented by the letter A. Now remember how the atomic number Z just counts the protons? Well, the mass number, A, gives us the total combined count of every single heavy particle inside that vault. It's simply your protons plus your neutrons, the whole payload. All right, let's look at Chapter 3, the particle math formula. Time for cracking the code. Here is the particle math formula, and honestly, it is beautifully straightforward. A equals Z plus N. Or in plain everyday English, the mass number equals the atomic number plus the number of neutrons. Think about it. Since we know the mass number represents everything inside the vault, and the atomic number is just the protons, finding out how many hidden neutrons there are is literally just basic grade school subtraction. It's that easy. And this brilliantly illustrates exactly how we apply it. Let's take aluminum. It has a mass number of 27 and an atomic number of 13. Just subtract 13 from 27, and boom, you get 14 neutrons locked inside its vault. But what about chlorine? Take a look here. You see a mass of 35.5, which would give you 18.5 neutrons. Now, hold up. You obviously can't have half a neutron. That 35.5 is actually just a weighted average of the different chlorine isotopes that exist naturally out in the world. But the formula itself, it works exactly the same way to pinpoint the particle balance for any specific individual atom. Which leads us perfectly into Chapter 4, solving the elemental puzzle. Let's read the subatomic roster. So let's look at how balanced nature can be. For a completely neutral atom, the number of positive protons is going to perfectly match the number of negative electrons. Take carbon, for example. An atomic number of 6 means 6 protons, which, because it's neutral, means 6 electrons. Its mass is 12, so 12 minus 6 leaves us with exactly 6 neutrons. Just perfect symmetry. Nitrogen works the exact same way. 7 protons, 7 electrons, and a mass of 14 leaves you with 7 neutrons. And chlorine? If we use a rounded mass of 35 for a typical isotope here, it's got 17 protons, 17 electrons, and subtracting 17 from 35 gives us exactly 18 neutrons. It is just remarkably beautifully consistent. But what happens when things change? Let's get into Chapter 5, Ions, Gaining and Losing, the Outer Shell Shuffle. So here is a fun plot twist. Let's examine sodium. Neutral sodium has an atomic number of 11, so 11 protons and 11 electrons. Simple enough, but when it becomes ionized to Na with a positive charge, that positive sign actually means it has lost one of its negative electrons. So its electron count drops down to 10. But look at the vault. Inside, it still has exactly 11 protons. The absolute core identity of that sodium atom hasn't changed one single bit. Now, let's flip it around and look at oxygen. Neutral oxygen is atomic number 8, meaning 8 protons and 8 electrons. When it ionizes to O-2, that negative sign means it actually went out and grabbed 2 extra electrons, so its outer electron count jumps up to 10. But once again, what's inside the vault? Safely locked away are those exact same 8 protons. And sulfur follows the exact same pattern. It starts neutral with 16 protons and 16 electrons. But when it takes on a -2 charge, it scoops up 2 extra outer electrons, bringing its total to 18. Yet its 16 protons, and its 16 neutrons for that matter, remain totally stable, completely untouched by the little electrical shuffle happening on the outside. Phosphorus works the exact same way. With an atomic number of 15, neutral phosphorus balances 15 protons and 15 electrons. If you spot a P-3 ion, well, you know right away it's gained 3 whole electrons to max out at 18. But again, it perfectly preserves its absolute core identity of 15 protons. Now, what's really interesting about this slide is how clearly it defines the absolute boundaries of chemistry. I really want this permanently etched into your mind. The electrical charge of an atom, whether it becomes positive or negative, is entirely 100% a game of electrons. The nucleus, that heavily fortified inner vault of protons and neutrons, completely ignores the electrical changes happening outside. The identity of the atom is entirely, permanently preserved. And that brings us to our grand finale, Chapter 6, the ultimate subatomic match, when N2 equals CO. Let's move to and see how this builds, because this is wild. Consider N2, right? That's just 2 atoms of nitrogen bonded together. Nitrogen is atomic number 7, meaning 7 protons, 7 neutrons, and 7 electrons. Double that up, and an N2 molecule has a grand total of 14 of each particle. Okay, now compare that to carbon monoxide, or CO. Carbon is atomic number 6, and oxygen is atomic number 8. Add those together, and what do you get? Exactly 14 protons, 14 neutrons, and 14 electrons. 2 completely different molecules with radically different chemical behaviors in the real world happen to share the exact same underlying subatomic math. It's honestly just an incredible coincidence of nature. Which brings us to a final provocative thought I really want to leave you with today. We've seen firsthand that the inner vault remains tightly locked, but those outer electrons? They are constantly in flux. So I pose this question to you. If electrons can come and go so easily, how much of the universe's incredibly complex chemistry is quite literally just atoms endlessly trading their outer shells to find a little bit of balance? Think about it. Thank you so much for joining me in this explainer today. Keep questioning, keep structuring that knowledge, and I'll catch you in the next one.